Hi, everybody. I am going to take you through another medium level difficulty optimization problem now, and I'd like to show that problem to you. The problem is question number 14, and it's really not that hard. It's fairly easy, but it's still, I think that the setup process of the question is one step up from the stuff you were doing yesterday with the grade 10 type problems. So the question reads, the volume of a closed cylindrical can is 25 pi meters cubed. That's the volume, that's set. So that's like a constraint. And then it says, find the dimensions that can minimize the surface area. So the surface area is the thing that we're going to be taking the derivative of or optimizing, and it's going to be constrained by the volume, okay? And so we're trying to minimize surface area. Now remember that it's a cylinder this time, okay? So cylinders have different formulas than boxes. And let's go ahead and investigate that now, okay? So what we'll do is we will go to a little note sheet here. And what we have is we want to remember that the volume of a cylinder is equal to the area of the base, which of course is a circle, times the height. So generally we like to work in terms of x's and y's. So what we'll do is we are going to always keep something very clear in the back of our mind, and that is the fact that when it comes to finding derivatives of functions, we want to work with a single variable. This is important because we're not at the point where we can do something called implicit differentiation, which is when we work with two different variables. We're not doing that. We're going to work with a single variable, and we are going to therefore have to make a few alterations, okay? So we're going to use our constraint equation, which relates to volume, in order to generate a surface area function that we will then optimize. And this will be a common theme that you'll see running through a lot of optimization problems. Let me repeat that procedure. We will use our constraint equation in order to generate our function that we will then use for optimization. Okay? And in the process of using our constraint equation, we will find a way to define all of our key variables in terms of one letter as opposed to two letters. Because as you see right now, as things are set up, we have two variables. We have r for radius and we have h for height. Remember, pi is not a variable, pi is a constant. Okay, volume, we know what that is, right? So let's go ahead and use our constraint equation to come up with a optimization function we can use for surface area. Okay, so volume, which is 25 pi, right? That was the volume, if you recall, that would have to be applied to this cylindrical container. 25 pi equals pi x squared times h. And of course, what I have just done there is I've said, let x be the radius. Okay. All right. So now this leaves us with two variables still, but now here's where the neat part comes in. We're now going to define height in terms of our other variables. Height will equal 25 pi over pi x squared, right? Now, height is defined in terms of x, which is a single variable, and we'll take that one step further, and we will say that we can cross out our pi's, and we will have height is equal to 25 over x squared. Okay, that leaves us with something we can work with now. Now, what are we trying to optimize? Well, if we remember what the question said, I'll read the question out to you again just so you can hear it. The question said the volume of a closed cylindrical can is 25 pi meters cubed. Find the dimensions of the can with a minimum surface area. Okay, well, surface area of a closed cylinder is equal to the area of the top and the bottom plus the area of the side portion or the lateral portion. So the surface area is going to be 2 pi r squared plus 2 pi r h. That is the formula for the surface area of a cylinder. But of course, we're going to modify that formula by plugging in the variables that we have defined according to our constraint equations. So surface area, in fact, will equal to 2 pi x squared plus 2 pi x. And remember what h was? H was 25 over x squared. Okay, this is the unsimplified form of the function that we're going to need to derive and optimize. Okay, but before we get to the process of actually optimizing it, let's go ahead and simplify it. So surface area will equal 2 pi x squared plus 2 pi. Now look at these x's, right? Check these x's here. We got an x and an x squared. That on the top is an x to the power of 1 over 2. So 1 minus 2 is negative 1. So what we actually have is 25 over x, right? Because just as an aside, right, think about it for a second. If you had x over x squared, that would equal x to the power of 1, right, divided by x to the power of 2, and that would equal x to the power of 1 minus 2, and that would equal x to the power of negative 1, which of course is equal to 1 over x. But in this case, it's not 1 over x, it's 25 over x. Okay, so just as an aside, in case you wanted a quick refresher on exponent laws, because if you don't remember those laws, obviously what I'm going to do there is going to seem confusing, okay? So then now we're going to take this another step further in terms of its simplification. I would suggest as a general rule, you want to simplify things quite a bit before you get to the point of deciding to take the derivative, because if you decide to take the derivative right away, you may find that the derivative gets prohibitively difficult. See what I just did there? I took 25 times 2, which is 50, and then knowing that I'm going to be using the power rule, I brought the x up to the numerator and made the exponent negative. And now, in my opinion, at this point in time, this is a surface area equation that we can work with. Now remember, the question said minimum surface area. So this is the thing we're trying to optimize, okay? So SA prime, oops, let's undo that, sorry. SA prime is equal to, power rule, 4 pi x. Okay, then look at the power rule in the second part. It's going to be negative 1 times 50. So negative 50 pi x to the negative 2. Okay, reduce the exponent by 1. Let's simplify that a little. SA prime is equal to 4 pi x minus 50 pi over x squared. Now from here, what we want to do is we want to take our derivative, and what I'm going to do is, we've taken our derivative, I should say. Now the optimization process, the minimum / maximum value occurs when you set your derivative equal to 0. And okay, so like when you think about it though, well, let's just think about this for a second. So I'm going to set this equal to 0. So let me get this out of the way and move it up again. So we're going to say now, 0 equals 4 pi x minus 50 pi over x squared. How do I solve this? Well, the first thing I want to do is I want to get rid of my x squared in the denominator. So I'm going to times the right side by x squared. I got to times everything by x squared. See, this is the problem. Times everything by x squared to get rid of my fraction. Now look, what we find is the following. We find that that cancels out. This x squared here will multiply by the x. And of course, 0 times x squared is just 0. So that cancels out. Here's what we have. We have 0 equals 4 pi x cubed minus 50 pi. Now we got to solve for x. Okay, well, easy. Let's move around here. And what we'll do is we will say now 50, just rearrange, 50 pi equals 4 pi x cubed. X cubed equals 50 pi over 4 pi. The pi's cancel out. X cubed equals 50 over 4. Well, what is 50 divided by 4? 50 divided by 4 is equal to 12.5. Okay, 12.5. Let's move over here. X is equal to the cubed root of 12.5. X is equal to, well, the cube root is the same thing as the power of 1/3, right? So the power of 1 divided by 3 bracket. X is equal to 2.32, approximately. So that's the radius of our cylinder. And if you recall, we can then figure out the height of our cylinder. And the height of our cylinder, right? Let's just move around here. Let's just remember what our expression for height was. Height was equal to 25 over x squared, right? Height was equal to 25 over x squared. Okay. So height equals 25 over, and we'll say approximately 2.32 squared, okay? Height equals, okay, so 2.32 squared is equal to approximately 5.38, and 25 divided by that is equal to 4.64. Okay, and then if we just remember what the question said find the dimensions. Well, the dimensions, therefore, according to our work, are equal to a radius of 2.32 and a height of 4.64. And those are the dimensions of the cylinder that will minimize cost given a set volume. Now, if you wanted to double check that it was a minimum, then all you would do is you would go back to the derivative, okay, and you would find the second derivative. And SA double prime, we would find would give us a positive result, right? It would give us a positive result. You can just do that as a mental exercise on your own if you wish. I didn't ask you to prove it, but you could take SA double prime, you'd get a positive result. And then you would find that if positive second derivative at a given value means a concave up, which means a minimum. Thank you, guys. That was a long video. I appreciate your patience. Nice work. And any comments you have, please feel free to ask.